So my group and myself, we are trying to really unravel the mysteries of the universe. And really what we are trying to do is find the deepest laws of nature. Now, how do we do that? Well, we do that by studying vases of flowers. This may sound a little crackpotty, of course, but bear with me. So the way we do that is this. Imagine you have a number of vases. No flowers, no water in there, sorry. Just the empty vases. And you have a spoon and you bang on the various vases one by one. Each one will make a sound as you tap it. The bigger vases will make a deeper sound and the smaller vases will have a higher pitch. Clearly, if you hear just the sound of a vase and you don't see it, you can already tell something about the size of it. But here's a much more sophisticated question, namely, if you just hear the sound of a vase, can you tell what the shape of it is in detail? Not just the overall size of it, but the shape of it. And that's a very old problem, it turns out. And recently we were able to basically solve that. And the trick we used was that we didn't try to solve the problem all at once. Instead, we cut it into small pieces. We solved the smaller problem of how the shape must have changed when the sound changed a little bit. So we calculated how a small change of shape is indicated by a small change of sound. And then you just iterate that until you get big changes of shape from big changes of sound. So basically you can relate the sound of an object to its shape. You may wonder, well, okay, it's good, but what does that have to do with the laws of the universe? What does that have to do with anything deep and fundamental? Okay, so for that I have to remind you that, there are two kinds of laws of nature out there that we know of. One kind of law of nature is concerned with stuff. It's concerned with matter, with how matter moves, how matter interacts with each other. And the second kind of laws of nature is about space and time. It's about the space and time in which all that material is moving. The first kind of law of nature is called quantum theory, and it is concerned with, as I said, everything that moves. Matter from atoms to stars, everything. And quantum theory has given us tremendous insights and tremendous applications. For example, the insights are that at the subatomic level, there's always a kind of quantum noise. There's always stuff going on, fluctuating. And on top of that, these fluctuations that are going on are actually without a cause. There are things happening that don't have a cause. Just like that. We can only give probabilities, but we can never predict exactly what's going to happen. Ponder that for a moment. What it means is that the laws of nature don't really tell us exactly what's going to happen next. There is some fundamental uncertainty in this. Okay, so quantum theory, this one kind of set of laws of nature, gave us this deep insight. It also gave us plenty of applications, from electronics to modern chemistry, modern biochemistry, and so on. Our life is longer and better because we understand those laws of nature. On the other hand, there are the laws of nature of space and time. General relativity, developed by Einstein. Also, that set of laws of nature has plenty of applications and deep insights. Deep insight, for example, is space and time are curved. Space is curved. The sun is curving space. And when the Earth goes around the sun, it's because it's following the curvature that the sun has created. The universe is expanding, and that expansion is technically the curvature between space and time. So lots of deep insights from that as well. And applications too. For example, the GPS unit in your phone is using general relativity. It's using that it knows how to calculate the curvature of space-time. It needs that in order to find out exactly where you are. So it all seems really great because we have these two sets of laws of nature. They are totally different, right? One is about space and time and curvature, and the other is about how stuff moves and quantum noise and whatnot. But both seem to be very successful. Give us insights, give us applications. Where's the problem? The problem is And when you look at those, and you study those two sets of laws of nature, you find that ultimately there are some circumstances where they contradict each other. Now, on one hand, you could say that's a huge crisis. On the other hand, you could say, hey, this is a fantastic opportunity because it means we haven't discovered the fundamental laws of nature just yet. We have some approximations, but they can't be the real deal because they are still not even consistent to each other. So that means it's a great opportunity. We can go out there and find better, deeper laws of nature that in one go describe the whole thing, matter and the space and time in which they live. That challenge has been out there for many years, and it's the last big frontier for physics. It's to find the fundamental set of laws of nature that combine general relativity and quantum theory. So what does that have to do with the flowers then, and the vases at least? Okay, so remember what we did there was we found a method to calculate the shape of vases from the sound that they make. See, the thing is this, the shape of a vase is really its curvature. And mathematically, that's the same kind of mathematics, right? Same kind of mathematics that is used for general relativity. So for this one set of laws of nature, the ones that describe space and time curvature. On the other hand, we have that the vase is vibrating. So there is matter which is moving and shaking and all that. The mathematics to describe how matter moves, well, that is the mathematics of quantum theory. That is the mathematics of the other set of the laws of nature. Even though it's very different, even though those two sets are very different, what we found here is a connection, a mathematical connection. The same mathematical machinery that we developed to calculate the shape of something from its sound can be used also to bridge from the laws of nature that describe the motion of stuff to the laws of nature that describe the curvature of space and time. Now, of course, we haven't finished this. All we did was find one piece of the puzzle there, and there is so much more to be discovered in that. And of course, everybody is very much invited to join in that search there, because who knows, once we find this final unifying set of laws of nature, what kind of even deeper insights we might find, and what kind of even more tremendous applications might flow from that.